Welcome back to Pentagram Prime, everybody. We will be trying something a little bit different in this episode, which I anticipate will drop on July 10th. Going to be, well, there isn't going to be as much animation in this episode. I'm going to be basically using notebook paper and one of my textbooks. This isn't the most interesting problem I could do, but it was one that I had in my journal of solved problems. And I'm using it basically as a test of the technique, how I'm going to choose to shoot today's episode. So today we will be solving problem number 148 out of Griffiths' Introduction to Electrodynamics, 3rd edition. This is on page 52 of that text. And what we're going to be doing is solving the integral, the volume integral J, which involves e to the negative r times the dot product of del and r hat divided by r squared d tau. In this case, V is a sphere of radius r, centered at the origin. And we're going to do it by two different methods, as described in example 16. Before I go any further, I wanted to say that part of the reason I'm using the methods that I'll be used today for photography and editing is that artificial intelligence is now taking over YouTube, unfortunately, and the more organic and human-like that I can make my videos look, well, it might be better off in the long run. I was originally planning to do this as basically no edits, one shot. My setup, it's not conducive to that right now, but I am going to be minimizing the number of edits. For one thing, the individual clips are not going to be cut up themselves. They are just going to be pasted together in the video editor, and you'll see that as time goes on. As I said, we will be using Griffiths' Introduction to Electrodynamics, 3rd edition, and I thought it would do us some good to take a look at the inside front cover, specifically the section involving spherical coordinates. We will be using the d tau for sure, and the gradient and the divergence. Curl and Laplacian I do not believe come up in this problem that much, but keep these figures in mind going further. They're not all in my notes, but they will be getting used. So the forgot what else I was going to say here, but that's what I get for not using a script. Also, a little bit of apology. My camera's focus is going to dip out occasionally, but hopefully it is close enough to focus to do the job. So going back to my notes, J is a volume integral where V is a sphere of radius r in spherical coordinates centered at the origin. So basically r is the distance from the origin. In this case, we have the divergence of r hat divided by r squared. And we'll be using two different methods. And now we're going to at least touch briefly upon example 1.16 on page 51, I believe. So we're going to take a look at example 116 on page 51. Keep in mind, this is not the problem we're solving. This is just an example that shows the methodology we will be using for problem number 1.48. In it, we're given, once again, volume integral, where V is a sphere of radius r at its origin. We have a function, r squared plus 2 over here, and we have divergence of r hat over r squared before the d tau term. we're going to end up using equation 199, which is on the previous page. And get this centered. All right, so right here. And basically that gives us a breakdown of the meaning of the divergence of r hat over r squared and how it is equivalent to a three-dimensional Dirac delta function. Going back to the opposite page, we see that if we follow the instructions from the previous page, what we end up doing is evaluating this function r squared plus 2 at the 0 point for the Dirac delta function, and 4 pi really is 4 pi times that function really is part of the result in that it comes outside of the integral. So we end up with 4 pi times the function evaluated at basically r equals 0, null vector, and we get 8 pi. It's a very simple solution. If you want to pause the video and read the text, I'm probably going to skim past that. Next we end up needing to use equation 1.59, and we're just going to go ahead and basically transfer the figures here to basically the formula that formula 1.59, which is shown on page 37, and I bookmarked it. Yep, 1.59 right here. So really the integral j that we're solving matches this, and we're going to be transferring f as well as the del dot a term into a form for the right side showing both volume and surface integrals. Go back to page 51. Or one page, go. All right. So if you look at formula 1.59 and sit down with the terms, you can see that the formulas for f and the term that is used for the divergence fit in here nicely, and then we go ahead and solve these two terms. Keep in mind that 8 pi is the method we got, is the solution we got with the original methodology. So we insert to the volume and the surface integrals. We then solve for the gradient, and then we start working on the volume integral, which in this case works out to 4 pi r squared. We then need to set up a term for dA, and from there dA is, well, it's dotted with the, dA is dotted with the term r hat over r squared multiplied times the f term, in this case r squared times 2. And we come up with 4 pi r squared plus 2. When the two terms for j are added up, the r squares drop out, or the 4 pi r squares dropped out, one negative, one positive, and we're left with 8 pi as before. So that's the method we'll be using for the for exercise. That's the method we'll be using for exercise or problem 1.48. All right, so in order to evaluate j, we're going to be using the two previously described formulas, some in the textbook. We're going to be using equation 199 in order to substitute in for the divergence of r hat over r squared, And you can see the direct delta function here for that. Evaluation of the direct function should give us the value of f, which in this case is going to be e to the negative r at what's basically the origin. In this case, a vector equal to 0, 0, 0 for x, y, and z. Keep in mind we're actually using spherical coordinates, so basically r equals 0. Focusing on solution 1 here. V, of course, as said, the volume of the sphere of radius capital R contains the center, so that we end up getting a value for e to the negative 0. Multiply that times 4 pi, and we get 4 pi. Easy peasy. All right, so solution 2 to exercise problem 148 is going to involve use of equation 159, which we just showed on page 37. For those of you who need to see it again, here it is. And we're going to use it to manipulate the integral j, which is at the outset of the problem is in this form, f times the divergence of A. But now we're going to go ahead and substitute the formulas as appropriate in the right-hand side. So the vector A in this case is r hat over r squared, dotted with the gradient of f, when for our purposes f is e to the negative r. Multiply that times the volume element d tau. Our surface integral will be f multiplied times the aforementioned a vector dotted with dA. Slide this forward. So dA, for our purposes, operating on the surface of a sphere of radius capital R, is going to be r squared multiplied times sine theta d theta d phi multiplied times the unit vector r hat, which is pointing radially outward from the surface of the sphere. This is shown on page 40, kind of, as is d tau. In fact, we're going to take a second, we're going to pop over to page 40 to show this. All right, so here on here on page 40, it is stated that for the purposes of integrating over the surface of a sphere, our dA is equivalent to r squared sine theta d phi multiplied times the unit vector pointing radially away from the sphere, and also illustration 1.39 is shown on the opposite page. Gives us an idea what we're talking about here. Don't need to worry about A2 right now. Just basically we're going to be focused on dA facing radially outward. All right, so I think that sums up what we need to discuss as far as the unit surface area, dA. D tau is covered on page 40. I didn't dwell on that because it's also covered on the inside on the inside front cover of the textbook. There's no d tau is a scalar, whereas dA is a vector. Our next step will be to go ahead and evaluate the individual integrals utilizing what we now know about d tau and dA. So in the first part of J, we will now be substituting in for the gradient of e to the negative r, and that works out to negative e to the negative e to the negative r multiplied times r hat, which we put up right here as noted by the asterisk. And we're also substituting in for d tau, which in this case is r squared sine theta, dr, d theta, d phi. On the second integral, this case the surface integral, we substitute in for, oops, I'm losing track of my terms. Let's see. Really, the only thing we're substituting in for here is dA. So dA equal to capital R squared sine theta, d phi multiplied times r hat. And we will be dotting that with the first term, or the vector r hat divided by capital R squared. The capital R is substituted in for the variable r, lowercase r, because we are only on the surface of the sphere, so there is no real r dependence. It is the only change is in the unit vector pointing radially out from the surface, whereas the distance is constant at capital R. And of course, we are integrating over a sphere. So in this case, theta goes from 0 to pi, and phi goes from 0 to 2 pi to complete the surface of the sphere. The evaluation of gradient of e to negative r, of course, has zero dependence on the phi and theta. I'll call them the phi and theta degrees of freedom. Those are zeroed out. The only variable that has any that is all can be have a derivative taken of it is the r is the component with r dependence, in this case e to the negative r. So that's how we end up with that. Moving on down, what we have now is we have r hat dotted with itself, which goes to 1. R squared is divided by lowercase r squared is divided by lowercase r squared. That did bother me a little bit, but really the any singularities at the center of the coordinate system, they're removable. So in all limits considered, it's not a factor as far as I can tell. So this goes to 1, this goes to 1, e to negative r times dr is still there. And then the evaluation of the theta and phi components is independent of evaluation of the r section. In the case of the surface integral, once again we have sections that separate out for theta, in this case sine theta d theta from 0 to pi, and d phi from 0 to pi with nothing except 1 for an integrand. E to the negative r has e to the negative r is constant, and r squared divided by r squared goes to 1, as does the dot product of r hat with itself. I did have some reservations about r squared divided by lowercase r squared divided by lowercase r squared, but I wouldn't worry about it. The more I looked into it, the more I realized that there's no issues there with it affecting the value of the integrand, or the value of the integration. So anyways, we evaluate negative e to the negative r across uppercase R and 0, multiplied times the results of these two integrals. The first one goes to 2, and the second one goes to 2 pi. So it goes similarly for the second integral. The integral of 0 to pi sine theta d theta goes to 2, and the integral of 0 to pi goes to 2 pi, and then we are left with a term e to the negative r. Combining like terms, we get a 4 pi multiplied times negative e to the negative r plus e to the negative 0 plus 4 pi times, the second integral goes to 4 pi times e to the negative r. The e to the negative r terms combine. The 4 pi e to the negative r terms combine. One's negative, one's positive, and they both cross out. We have a 4 pi times 1, and that is the same as the solution that we got on the previous page of my notes. Let's see. Solution, whoa, this thing lined up. Solution to, solution 1 gives us 4 pi, and on the opposite side, the second solution comes out to 4 pi. So I appreciate those of you who viewed and stuck through to the end of the video. I understand this format is a little bit rougher, a little less polished, and if I got anything wrong or did anything I shouldn't have done, I am available in the comments. I gotta say, I don't respond to every single comment because a couple of times I've had people posting comments in there. I swear to God, I had no idea what they were talking about. And I'm not sure if they did either. So I just, I think I wrote back in 1 or 2 cases, and that's just clarification. But yeah, just give me a clearly worded answer, and I'll do what I can for you guys. I prefer this method simply because it's 1 day of production versus 7 months of production, which is what happened with the previous video. And that way I get to do more problems and pick out the ones that are more interesting. So till next time, this is Pentagram Prime signing off.